So today we're going to look at solving linear systems, which you actually did in Algebra 1. So this section really will be reviewed, but you may not remember it that well. And if you didn't get fairly proficient at graphing lines in the last chapter, you need to get proficient graphing lines by this chapter because it's going to be a huge part of it. So when we're talking about solving a system of linear equations, we are looking for where those two linear equations are equal. So when we're talking about solving it graphically, it's going to be where those two equations intersect in the coordinate grid. And then we're going to look at solving them algebraically, and solving them algebraically means that you're going to use substitution or elimination. So new vocabulary, our break-even point, that's essentially where the two lines are equal to each other. System of equations, any group of linear equations. We'll talk about consistent, inconsistent, independent, dependent, substitution method, and elimination method. So let's first of all start by solving the system of equations by graphing. And so I'm going to go ahead and pull up my graph. And both of these equations are in standard form, but unfortunately this first equation, it doesn't help to graph it using the intercepts because the intercept is 0, 0. So it's not going to help us in the slightest to find both intercepts. So instead, I'm going to take this first equation and I'm going to get it into slope-intercept form. So x minus 2y equals 0. We get negative 2y equals negative x when we subtract x from both sides. And then we divide by negative 2. So we have negative x over negative 2. So y equals positive 1/2 x. So we have a y-intercept of 0, which we knew. And then we have a slope of 1/2. So about like that. And let me pull up my handy-dandy line feature. Oops. And so we have that for that first line. And then for the second line, it is easy to find the intercepts, and I'm going to do this one in blue. So for this one, I can either get it into slope-intercept form, which is y equals negative x plus 6, or I can find the intercepts, which would be 0, 6, and 6, 0. Either way is fine. So I know that the y-intercept is 6, and I know that this one is 6, 0. I know it has a slope of negative 1, and so that will work beautifully. Handy-dandy line feature. There. And so what we see is we see a solution that's equal to 4, 2. Now I'll go ahead and do that in purple since we have. So graphically, that's how you would see the solution. Now, when two equations only have one solution, I have to see. When two equations only have one solution, this is called a consistent and independent system. Consistent basically means it has at least one solution, and independent means that there is one solution when we're talking about systems of linear equations. Okay, graph a system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. Well, consistent and independent, we just said, that means that it has one solution. Consistent and dependent, that's going to mean that it has infinite solutions. And basically what that means is that it's the exact same line. And inconsistent means that it has no solutions or an empty set. Now, the way you can write empty set is that 0 with a slash through it. Please don't use that as a 0. I see some people doing that sometimes, and that means that there's no solution. And if you have an inconsistent system, it means that you must have parallel lines because they would never intersect. So let's go ahead and solve this system, and they want to do it by graphing. So we have x minus y equals 5. If we get that into slope-intercept form, we're going to get negative y equals negative x plus 5. Oops. And then we're going to divide by negative 1. So we get y equals x minus 5. So slope-intercept of negative 5, and it has, the y-intercept of negative 5, and it has a slope of 1. So it's going to be that line. And the other equation, we have 2y equals, whoa, don't know what's happening there. 2y equals negative x minus 4. Divide by 2, divide by 2. We get y equals negative 1/2 x minus 2. So that's going to be here. And then negative 1/2 x. Pretend that looks good, and pretend that you can actually see that it's intersecting right there at 2, negative 3. So it has exactly one solution. So we go back up here and we say, okay, then it is consistent and independent. Okay, graph the system of equations and describe it as consistent, independent, consistent, and dependent or inconsistent. I'm going to go ahead and get this line in slope-intercept form. So we get negative 6y equals negative 9x minus 6. Divide by negative 6. And we get y equals 3/2 x plus 1. And then for the other line, we get negative 4y equals negative 6x minus 4. Divide by negative 4. And we get y equals 3/2 x plus 1. So algebraically, we can pretty much see that we have the exact same line here, but they wanted to show it graphically, and so that is what we will do. Oops. And we'll do it in purple. So 3/2 x plus 1. So we want to rise 3, run 2, or go down 3, back 2. And both of these lines would end up graphing just like that. So it has infinite solutions. And therefore it is consistent and dependent. So going up here, it's consistent and dependent. All right, graph the system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. So let's get rid of the solution that I accidentally posted there. So putting this into slope-intercept form, we get negative 6y equals negative 15x, and divide by negative 6 on both sides, and we get 15 over 6, which would be by 3, 5/2 x. And then when we do the other one, we get negative 2y equals negative 5x plus 10. Divide by negative 2. And y equals 5/2 x plus 5. So we look at the slopes and we should know that these lines are parallel. And so when I graph the red line, whoa, that was bad. That wasn't much better, but I don't feel good, so I'm not going to mess with it. And then the other line is here and here. well, those essentially look parallel. So there are no solutions here, so it is an inconsistent system or an empty set. Okay, we're not going to graph these. I just want to look at these algebraically. And so if we look at f of x and g of x as being a system, what kind of system is it? Well, we know that we have the same slope and the same y-intercept, so this would be consistent independent. It would have infinite solutions. But what if we look at f of x and h of x as a system? So in this case, all we have to know is that they have different slopes. And when two lines have different slopes, they're going to have exactly one solution. So it's going to be consistent and independent. And what we don't have here is we don't have one that would be inconsistent. And so what I'd like to do is I'd like to make up another function, and I'm going to call it j of x. And I want to come up with a j of x so that if I combine it with one of these other lines, I have an inconsistent system. And I'm going to look at j of x and f of x. So to have an inconsistent system, I need to have the same slope and a different y-intercept. So now I can say that j of x and f of x are inconsistent because they have same slope and different y-intercepts, so they will never intersect. So here is the summary of those systems that we just talked about. So intersecting lines have exactly one solution, same line has infinite solutions, and parallel lines have no solution. So now we're going to look at the substitute method, substitution. And substitution is a good one to use when it's very easy to get one of the variables by itself. And then you can just put that into the other equation. So let's look at an example of this. Lancaster Woodworkers Furniture Store builds two types of wooden outdoor chairs. A rocking chair sells for $265. So we'll write R is going to be our rocking chair. An Adirondack chair with footstool sells for $320. The book show last month that the business earned $13,930 for the 48 outdoor chairs sold. So how many of each were sold? So we have a system here, and what you need to do is, the hardest part of systems is coming up with an equation from a word problem. But this is an incredibly good life application problem because anytime you're dealing with any type of business, they have to think about this all the time. What is going to bring them the most profit? That's almost always involving a system of equations. So in this case, we're going to look at one equation is going to involve only the numbers of chairs sold, and the other equation is going to involve only money. And so the easy one is just the number of chairs sold, and that's just R plus A equals 48, sheer numbers. Second one is dealing with money, and for every rocking chair they sold, they made $265, and for every Adirondack chair they sold, they made $320, and they made a total of $13,930. Now this is a great one to use substitution for because with this equation I can get either R by itself or A by itself, which makes it really easy to substitute into the other. It doesn't matter which one you do. So I'm just going to do R equals 48 minus A. And so I'm going to take this and I'm going to substitute it in for R in this equation. So we're going to get 265 times 48 minus A plus 320A equals 13,930. And you'll know if you've substituted correctly because when you do, you should only have one variable left in your equation. So when you multiply 265 times 48, get 12,720 minus 265A plus 320A equals 13,930. So we want to subtract 12,720 from 13,930. So 1,210. And negative 265 plus 320 is going to be 55A. So divide by 55. And we get 22. So they must have sold 22 Adirondack chairs, and then you go back and you substitute that into the easier of the equations, which is definitely that one. And so you get R plus 22 equals 48. So they must have sold 26 rocking chairs. And so you would want to summarize your answer and label it, telling me that they sold 22 Adirondack chairs and 26 rocking chairs. And I'm writing with my finger right now, so it would take me a while to do that, but know that you should always label your answers in word problems. Okay, elimination is when you have to multiply one or both equations by a number to result in two equations that contain opposite terms. And then you add the equations eliminating one variable and then solve the equation. So use the elimination method to solve the system of equations. And so in this case, it's actually really easy to eliminate x's, but I want them to have opposite signs so that I can add them and eliminate it. So I'm going to multiply that bottom equation by negative 1. And so when I do that, I haven't touched the top equation. I just get x plus 2y equals 10, and then negative x minus y equals negative 6. And now we add them. X plus negative x is 0. They're gone. 2y plus negative y is y. 10 plus negative 6 is 4. So we now have that y equals 4. And now we go and substitute in. And I like this equation better. So I'm going to say x plus 4 equals 6 and x equals 2. Now you should always give me an ordered pair. So we have 2, 4 would be the solution to this system of equations, and it's a consistent independent system. Now sometimes you have to multiply both equations by something, and so when I'm looking at this one, I see that the coefficients in front of y have opposite signs, so I'm going to work with that so that I don't have to multiply by any negative numbers. So if I want to get the coefficients to be opposite of each other, I'm going to multiply 2, and I'm going to multiply the bottom equation by 3. So when I do that, I get 4x plus 6y equals 24. Down on the bottom, I get 15x minus 6y equals 33. So now I can add them, and those y's are going to be eliminated. And when I add them, I get 19x equals 57, and x equals 3. So I can already tell that the answer is going to be D based on what they've given me. But I'm going to go ahead and plug that in I'll plug it into the first one. So 2 times 3 plus 3y equals 12. Subtract 6 from both sides, we get 3y equals 6, and y equals 2. So that just confirms that our answer is D. It's always good to go and plug it into the other equation, the 5x minus 2y equals 11, and make sure you get a true statement, because then you're certain that you're right. So this is just summarizing what we've already talked about, the different ways to solve systems of equations. And then section 3.4, we're just doing 2 problems from section 3.4. I think what we're going to do is next class, I'm going to have you guys solve this in your groups because it's a fun one. So just do section 3.1 from your syllabus. And don't worry about the section 3-4 yet. Thank you.